All right, so I'm going to talk about the response of higher order systems. So far we have discussed both first and second order systems, and meaning the system has either one pole or two poles. So we have to emphasize that the formulas that describe the percentage of overshoot, settling time, and peak time associated with second order systems were derived specifically for a system that only had two complex poles and no zeros. So now if a system has obviously more than two poles, or a system has a zero, then most likely those equations are not actually going to be useful. So however, under certain conditions, a system with more than two poles, or even a system with a zero, can be approximated as just simply a second order system that has just two complex, what we call dominant poles. Okay, and so once we justify this approximation, then all the formulas that we have so far derived and used for percentage of overshoot, for example, settling time and peak time, can be applied to even those high order systems. So in this section, I'm going to examine the effect of an additional pole on the second order system response. And then in the next section, the next part of this lecture, I'm going to talk about the effect of a zero. So now let's consider a second order system, well, actually a third order system that has a pair of complex conjugate poles that is actually described by this s squared plus as plus b, and another simple pole at s equal to negative c. So now we actually want to examine the conditions under which this second order system can be approximated by, this third order system can be approximated by a second order system, meaning just this part, s squared plus as plus b in the denominator. So now let's examine the step response. So we have learned that, in order to find the step response, what we do first, we have to find the Laplace transform of the response, which is going to be y of s equal to r of s multiplied by g of s, and if r of s is just 1 over s because that's a step input, then the y of s is just going to be this g of s, and it also has an s in the denominator. Then if we apply partial fraction expansion, it's going to be represented in this form, and as you see, this s squared plus as plus b can be if you just write it as a complete square, it's going to look like this. So basically that just tells you that the system has three poles, one at negative c and the other two at negative zeta omega n plus minus j omega d. So now let's just establish conditions under which we can approximate the response of, well, we can approximate this system g of s, which has three poles by just simply two poles. So now this here it shows the step response. After you convert that y of s back to time domain using inverse Laplace transform, the response is actually going to look like this. So as you see, we have this part which is very similar to the response of a second order system, and we also have this part which is very similar to the response of a first order system. That is because of that term s plus c that we had in the denominator. So now as you see, the contribution of that extra pole, which was negative c, or we actually characterize it as negative alpha r, would be this. So now, in order for this part to be negligible compared to the response of the second order system, we must ensure that this part of the response dies out much more quicker compared to this part, because if that approximation can be held true, then we can just ignore this part and we can just approximate the response by this part, which is only representing the response of a second order system. So now this shows, this is actually an illustrative example just showing how the response is going to change in terms of the location of that extra pole compared to the location of the complex conjugate poles. In fact, we can distinguish three cases: case 1, case 2, and case 3. So in case 1, we see that these are actually the two poles associated with the second order, the complex conjugate, and this is that extra pole. So now in case 1, as you see, that the extra pole is actually kind of close to the complex conjugate poles. So in case 2, it just moves a little further away from these two poles, and in case 3, that pole is not even shown because that's just too far. It's just like here, that's just too far away from these two poles. So now these plots that you see here, there are actually two groups of plots. One is what you see up here, and the other one is actually here. So now it shows that for case 1, the response of second order part is actually going to look like this. For case 2, it's going to look like this, and for case 3, it's going to look like this. So now if you compare the responses of that extra pole, or the response due to that extra pole, it's actually going to look like this. So in case 1, it's like this. So it actually takes a while for the response to die out. For case 2, it dies out much more quicker. And case 3, you don't even see that, but it actually looks like this. So it's just that red line. So it just starts from almost close, and in no time it just gets to a steady state. So now and that's actually obvious because you remember the time for first order systems, we actually define something called time response, or time constant. So time constant, we just indicate how quick your response of the system or step response is actually going to reach to a steady state. So now, and if you recall, the time constant was the inverse of the pole. So if the pole was just too far from that imaginary axis, then the inverse of that number is just going to be very small. And therefore, it's actually going to and therefore your time constant is small, and hence your response is actually going to be very quick in terms of reaching that steady state. So now, the bottom line here is that if your extra pole, that extra simple pole, is actually much further away from this dominant, what we call dominant complex poles, then we can approximate the response of that third order system by just simply the second order system. So now the next question is, how much farther from the dominant pole does that third pole have to be for its effect on the response to be negligible? So a rule of thumb is that it has to be 5 times farther. And for example, if you have a pair of complex poles, let's say -1 plus minus J2. If your simple pole is, let's say, at -2, then you cannot ignore the effect of that extra pole. But if the extra pole is, let's say, at -10, you can actually ignore the effect of that extra pole, because this is definitely less than 5 times farther away. So you just have to compare the a real part. You don't really look at the imaginary part. You just look at the real part. For this one, it's definitely more than 5 times further away. So now this is actually an example. So T1 of S is just a second order system. T2 of S is the same second order system, except that it has an extra pole at -10, and the third one, it has an extra pole at -3. So the poles for T1 are just -2 plus minus J 5.53. For T2 and T3, they actually share the same 2 poles, but T2 has 1 extra pole at -10, and T3, so T3 has an extra pole located at -3. So now you see that the gains are, the numerator are actually different, and the reason for that is that we want to normalize the response, meaning that we want the step response to eventually reach to the same steady state point. In order to do that, we have to ensure that the so-called DC gain, meaning the value of the transfer function at s equal to 0, is actually going to be the same. So at s equal to 0, the value of transfer function here is just 24.5 divided by 0 plus 24.5. So the gain is really just 1. So for T2 and T3 to have the same gain, here if we add this extra pole, we have to, so there's still going to be this number 10 that is going to be multiplied by the gain of the numerator of the denominator. So you just have to multiply this number by 10. For this one, you actually have to multiply it by 3 anyway. So for all of them, the DC gain is just 1 in order to maintain consistency in terms of for all of them reaching to the same value of steady state. So obviously, as you see, in T2, that extra pole is exactly 5 times further away compared to P1 and P2. And in T3, that extra pole is -3, which is not really 5 times further. So we should expect that a second order approximation would hold true for T2, but not, I'm sorry, for T2, but second order approximation is not likely going to work for T3. And that is exactly what you see in the next slide. So this next slide, I have plotted the responses using step command in MATLAB. So this is for the first order system. I'm sorry, C1, that's just the original second order system response. C2 is the original second order plus an extra pole at -10, and C3 the same poles plus an extra one at -3. So as you see, the responses of C2 and C1 are kind of more similar compared to C3. So now here, if that extra pole is actually located even further away from the complex poles, then it turns out that these two responses are actually going to become very, very similar. So the next thing I'm going to talk about is the effect of zeros. So the effect of a zero in response. So now the zero can be actually located in left half plane or LHP, or right half plane or RHP. And so if you have a zero that is located on the right half plane, we call that a non-minimum phase system, or NMP. And the reason why it's called non-minimum phase is something that we're actually going to discuss later when we talk about the gain margin and the phase margin of LTI system. So that's not something that I can actually talk about right now, but perhaps in a month we're going to be ready to even talk about that. So now let's consider that you have a transfer function Gn that has no zero, and you consider that you just add 1 0 to that, and that location of that zero is just at s equal to -a, and therefore you have another transfer function G of s, which is the same transfer function, which shares the same transfer functions. Which shares the poles of the same transfer function Gn. And as far as the zero, it just has 1 0 located at s equal to -a. So then in that case, in order to find the, let's say, step response, the step response are also going to be following exactly the same equation. So your step response is going to be C of s equal to s plus a multiplied by Cn of s. So Cn is the Laplace transform of the step response of Gn, and C of s is the step response of G. So now C of s is going to become Scn of s plus a Scn of s. So now if you do an inverse Laplace transform, inverse Laplace of this is C of t. If you remember, inverse Laplace of Scn of s would be just Cn dot, the first order derivative, and then this is just a scaling. So now, what does this equation tell you? So it tells you that if a is large, then of course you can just ignore the derivative term, meaning that so the response of the system with a zero is just going to be a scaled a version of the response of the system with no zero. But again, this is going to be true only when a is large. But when a is not large, then both a Cn and also the derivative of Cn or Cn dot are actually going to contribute to the response. So now let's look at an example. So let's just consider this transfer function 9 over s squared plus 2s plus 9. So obviously this is a system with a DC gain of 9 over 9, which is just 1. So you really expect that your step response would eventually reach 1, which is exactly the case here. And it's a second order system with a pair of complex poles. And now for G of s, you assume that you have 1 0 added to this Gn. So now we're just going to examine 3 different values for 0. So now so the blue that you see here, that actually shows the response of the system Gn. So this is actually the response of the system. So this is the response of the system Gn. Okay, no zero. And then you obviously have 3 other plots. Each of them is associated with a different value of 0. So now, if your 0 is located at -10, that's what you get. If your 0 is located at -5, that's what you get. And if your 0 is located at -3, that's what you get. So the conclusion that you can arrive here is that if the location of the 0 is just too far away from the location of the pole, meaning that if the value of A is just too large, your response is actually going to be very similar. In this case, it's going to be very similar to the response of the system Gn with no 0. And if you just go closer, if you just come closer to the j omega axis, meaning that the value of 0 decreases, then the contribution of the 0 actually becomes much more significant in the response. So in the step response of the system. Okay. So for example, as you see, when 0 is located at -3, you actually see that the peak time has decreased significantly compared to this, and also the peak value has increased significantly. So really the peak occurs sooner, but the value of peak is going to be larger. So again, the conclusion we made was that with a 0 at left half plane, meaning that if you have a 0, if you have a simple 0, just the negative number, -1, -2, -10, -50. So you're actually going to have that maximum peak of the response. So that peak is going to happen sooner, meaning that your peak time is going to be smaller, but the value of peak is going to be larger. And that's exactly what you saw in the exam. So now, if you have a 0 at right half plane, so in S plane, I mean, if you just if I'm just going to show it, so if I have a pair of poles, complex conjugate, and just have one 0, and that 0 is located at right half plane, so what we're actually going to observe in the response is what is called undershoot. And that's something that I'm going to show you in the next slide. All right, so now this is actually an example. This is a typical step response of a non-minimum phase system, meaning that that's a system that has a 0 located at right half plane, or RHP, meaning it's just a 0 that is positive. So your 0 is like a 2, 5, 10, 20, whatever. So it's actually at the right half plane. So so now what you see here is that the response actually shows what is called an undershoot, meaning that if you recall previously, the response to a step would just ramp up even from the very beginning. But now if you have a non-zero, or rather if you have a non-minimum phase system, or with a 0 in the right half plane, then at the very beginning the response of the system is actually going to come down, and then it's going to ramp up. This is actually what is called undershoot. So now really the question is, why does this undershoot happen? So if you remember, we had this equation. So if you remember, we actually had this equation as far as relating the response of a system with a 0 located at A with a system that had no 0. Let's just call it Cn. So now if the value of A is negative, which represents a non-minimum phase system, so we actually, for example, we have Cn dot minus, let's say, 5 Cn. Okay, so it turns out that the very first few millisecond or first few second, I mean, just depending on how fast your system dynamics is, this term Cn, or rather ACN, is actually going to be much more dominant compared to Cn dot. So meaning that the value of the derivative at the very beginning is not as significant as the value of ACN. And therefore, of course, ACN is going to be dominant. And since the value of A is negative, then we're actually going to have Cn dot just going to become less and less and less compared to ACN. And therefore, your C of T is actually going to be negative for a while. And that's exactly why you see this undershoot. But after a while, it's just going to, like, I mean, the trend is actually going to be reversed, and Cn dot becomes comparable compared to ACN. Well, yeah, so it becomes comparable to ACN, and then the response is actually going to ramp up and eventually just behaves just like a regular second order system response. And the very last topic I'm going to talk about, finishing up chapter 4, is what is called pole zero cancellation. So it turns out that you can cancel out the effects of a pole and a zero if they are located very close to each other. For example, if you have a pole, if you have two systems, G1 and G2, so in the first system, you actually have a pole at -4, a zero at -4, and three poles, -5, -6, and -3.5. So you have another system, G2, that has the same zero and the same, well, the two poles are actually shared with G1, and you also have an extra pole that is at -4.01. So it turns out that, and that's something that you can show graphically, or you can just plot it in MATLAB to see how close the response actually look like. But it turns out that you can approximate the second system G2 by just simply eliminating S plus 4 and S plus 4 and S plus 4.01. So you can just simply cancel these two out. And the reason for that is that the location of the pole and location of zero are actually very close to each other. So you cannot really do that here because you actually have here -4 and -3.5. So they're still, well, they're still close, but they're not really that close. And so this pole is actually going to have its own effect, and also the zero is going to have its own effect. So now the important thing is that you can do pole zero cancellation if the location of pole and zeros are very, very, very close to each other. For example, if this 4.01 was like 4.02 or 4.03, that would be still okay to just make the approximation, like perhaps by maybe 0.5%, like 1%, that's fine. But you really cannot do that for, let's say, 3.5 and 4. You cannot really make the approximation. So now this actually gives you another way to approximate the response of systems. Well, the response of higher order systems. So for example, okay, so for instance, you can have a system that has, let's say, one zero and 4 poles. Okay, so now if one pole and one zero are actually very close to each other, you can just cancel them out. So now you can approximate the system by a third order system. And then if the location of that third pole compared to the complex conjugate poles is too far, meaning that if the complex conjugate poles are just dominant compared to that third pole, you can easily approximate that system by now a second order system. So I'm actually going to give a couple of in-class exercise problems to just demonstrate that.